Hey guys, Mr. Betts here. I want to talk a little bit more about conditional convergence and specifically rearranging terms in a conditionally convergent series. This is one of the more fascinating things I think about infinite series is what we can do with the conditionally convergent series, and it's really counterintuitive what we're going to be able to do with it. So I'm going to use as an example the alternating harmonic series, but I want to be clear that this is something that we can do with any conditionally convergent series. So the alternating harmonic series is conditionally convergent because if we look at the absolute series, which is what we would get if we just add all the terms together, that series diverges. So it has an infinite sum. So the alternating harmonic series we say is conditionally convergent because it converges by the alternating series test, but the absolute series itself diverges. So what does that mean? What that means is we can actually rearrange the terms in this series to make the sum anything we want. All right, so this is a really weird idea. If we add the terms together in order, this sum ends up being the natural log of 2, which is about 0.7. But we can make this sum add up to any number we want. We can make the sum equal to 1 if we want, or we can make it equal to pi if we want, which is the example I'm going to use here. So I mentioned this is a kind of counterintuitive idea. And the idea here is we're going to come up with this process that if we add all the terms together, but just in a different order than they are now, then we're going to get a sum that is pi. So the idea here is, first of all, we're going to put the terms into basically two piles. We're going to have a pile of all the positive terms, and we're going to have a pile of all the negative terms. And what we're going to do is we're just going to select terms from each of those piles as we need them. But the key is we're going to end up using all of them. All right, so the big rule for rearranging the terms is that we still have to add up all the terms. So our process has to include everything. We can't just say, okay, we're going to add up all the terms, but we're never going to include that -1/2 in the process, or we're never going to include the 1. We have to include every term in this process. All right, so here's how we're going to do that for pi. We're going to think of the positive terms and the negative terms, and to make this sum add up to pi, we're going to add positive terms until our partial sum is greater than pi. Then we're going to add negative terms until our partial sum is less than pi, and we're going to repeat. So a couple of things to keep in mind. One is each of these piles has infinitely many terms in it. So no matter how many terms I take out of this positive pile, we're always going to have more terms. And the same thing's true for the negative terms. No matter how many terms I take out of that pile, we're always going to have another one. All right, the other thing to keep in mind here is that because this is a conditionally convergent series, these subseries, the series of all positive terms and the series of all negative terms, actually diverge themselves. So the sum of all the positive terms is actually infinitely big. The sum of all the negative terms is infinitely big but negative. And that's actually a really important part of this. And that's going to guarantee that this process works. Because knowing that that sum is infinitely big, we know that we can add enough terms from that pile to make the sum as big as we want. In this case, we want it to be bigger than pi. All right, and then once we have a sum that's bigger than pi, we need to be guaranteed that there's enough terms in this negative series that we can make that sum less than pi. So knowing that each of these series individually is going to be an infinite sum, infinitely positive for the positive terms and infinitely negative for the negative terms, allows this process to work. And this repeat here, that's going to be an infinite repeat, which means that this process ultimately is going to get every term. So no matter what term I pick, whether it's a positive term or a negative term, eventually we're going to get to it because we're going to repeat this process infinitely long. All right, so here's what that's going to look like. Just the first step, add positive terms until the partial sum is greater than pi. We actually need the first 76 positive terms to make our sum bigger than pi. So after 76 terms, we get a sum of 3.147 and so on. And then we're going to add negative terms. It turns out that because the positive terms have gotten so small at this point, we haven't used any negative terms yet, so the next negative term is going to be -1/2. Pretty big relative to the terms that we've been adding. So we're going to subtract, and that's going to give us a sum that's less than pi. So we go from a number that's just a little bit bigger than pi to a number that's really significantly smaller than pi. And then we repeat. So we go back to the positive terms, and we're going to add on 1 over 153, 1 over 155, 1 over 157, and we're going to keep adding those positive terms again until we get to bigger than pi. And then we're going to subtract the next negative term and keep going forever. All right, so here's the graph of the partial sums to the first 100 partial sums. And notice that out of the first 100 terms, we're adding 99 positive terms and 1 negative term. So that negative term is being added right there where we see that dip. So we already talked about this, but the 76th partial sum is slightly bigger than pi. We add on the 77th term, which is going to be the negative 1/2, the first negative one from that pile, and then we get a partial sum that is 2.64. So then we start adding more. So we're adding on the 1 over 153, 1 over 155, and so on. So if I expand this from the first 100 terms to the first 1,000 terms, we can see that in the first 1,000 terms, there's 7 negative terms that we add on every time we get to one of these dips here. And then after we subtract one of those negative terms, then we're adding the positive terms so we get bigger than pi again. So you can see here that the minus 1/2 happens right here. The minus 1/4 happens here. The minus 1/6 happens here. This is going to be minus 1/8, minus 1/10, and so on. So no matter what term we pick, so say the minus 1 over 100 term, eventually we're going to get to that. So again, we're following that rule that every term has to be used. It doesn't matter that we're using more positive than negative, because eventually we're going to use any negative term that we choose. So if I expand this to 5,000 terms, now 37 out of the first 5,000 terms are negative, and almost all of them are positive. And if I zoom in on this a little bit on the graph, we can see that it's zeroing in on pi a little bit more. So every time we get a little bit bigger than pi, we subtract a negative term, and we keep the process going. So eventually this is going to get closer and closer and closer and closer to pi, because the terms that we're adding and subtracting are getting smaller and smaller and smaller. So we're going to be zeroing in on pi. And so the limit of these terms using this process is going to equal pi. So the limit as n approaches infinity of our partial sums in this process is pi, where when we didn't rearrange, it was the natural log of 2. I chose pi here, but we could do this with any constant that we want. So if I say that I want the partial sum to be, say, negative pi, we wouldn't start with any of the positive terms. We would actually start with negative terms until we get less than negative pi, and then we would add a positive term, and then we would subtract the negative terms until we get less, and then we would add a positive term. So we can follow this process with any number. We just add until we get above, and then we subtract until we get below. And using that process, we end up using all the terms, and we can make this sum anything we want it to be. Kind of a crazy idea. One thing to keep in mind is this is not something that's going to be tested, but it is important that you understand what it means to be conditionally convergent versus absolutely convergent. So if a series is absolutely convergent, then the sum is the same no matter what. So if a series is absolutely convergent, no matter how you rearrange the terms, if you add them all together, you get the same thing. If it's conditionally convergent, you can make the sum anything you want it to be.